Hello students, welcome back to my YouTube channel Ritika Chemistry Classes. I request you all to subscribe my channel to stay updated. Thank you. So now let's start. In the previous lecture, we studied about limitations of Bohr's model of atom. Although there are many limitations of Bohr's model of atom, but the main drawbacks which led to the foundation of quantum mechanical model of atom was that the Bohr's model failed to explain de Broglie's dual concept of matter and Heisenberg uncertainty principle. So we have already studied de Broglie's dual concept of matter, de Broglie's dual nature of matter. As we know that light possesses dual nature, that is, it behaves like particle as well as wave. So Louis de Broglie advanced this idea to all material particles, and he stated that all moving particles have a wave associated with it, and that wave is known as either matter wave or de Broglie wave. Then we derived the formula for the wavelength of this de Broglie wave, which is lambda equals to h upon mv, where h is the Planck's constant, m is the mass of the particle, and v is the velocity with which it is moving, and lambda is known as de Broglie wavelength. And you also know that mv is momentum, so lambda can also be written as wavelength lambda equals to h upon p. So then now today's topic is Heisenberg uncertainty principle. Write down Heisenberg uncertainty principle. So this Heisenberg uncertainty principle was given by Werner Heisenberg in 1927. According to Heisenberg uncertainty principle, it is not possible to determine simultaneously the exact position and momentum of a small moving particle. Write down. It is not possible to determine simultaneously both the exact position and momentum of small moving particles. That means if the particles are very small, so we cannot determine its exact position and momentum with high degree of accuracy. There would always be a small amount of uncertainty associated with both of them. Mathematically, if we want to write this mathematically, it can be written as delta x into delta p, that should be greater than or equals to h upon 4 pi. H is Planck's constant. We have already discussed it many times. And this write down delta x is the uncertainty in the position of particle uncertainty in the position of particle, and delta P, or more accurately you write it delta Px. Okay, if here we are taking x coordinate, then the momentum will we will also take the x coordinate of this momentum Px. Delta Px is the uncertainty in the momentum of particle. Right? So, and you know that momentum is equals to product of mass and velocity. So this delta Px can be written as m into delta Vx, which is greater than or equals to h upon 4 pi. Or you can write delta x into delta Vx, that should be greater than or equals to h upon 4 pi m. So these are the two expressions of Heisenberg uncertainty principle. Write down delta Vx is the uncertainty in the velocity of particle. Delta Vx is the uncertainty in the velocity of particle. Okay, you can also write here that it is not possible to determine simultaneously both the exact position and momentum, or you can say or velocity of small moving particle. So this is the mathematical expression of Heisenberg uncertainty principle. According to this expression, you can see delta x is inversely proportional to delta Px. Okay, you can see from this expression that delta x is inversely proportional to delta Px. So, if we want to determine the position of the particle with high accuracy, one second. So right now, if delta x is small, if delta x is small, what does delta x small means? That means the position of particle is known with high degree of accuracy. Is known with high degree of accuracy. Right? So if value of delta x is small, that means uncertainty in the position of particle is small. That means we know the position of particle with high accuracy, and you also know that this delta x is inversely proportional to Px. So small delta x would imply large Px, delta Px. Large value of delta Px. And large value of delta Px means there would be large uncertainty. There would be large uncertainty in the momentum of particle. In the momentum of particle. So, if we want to measure the position of the particle with high accuracy, then what will happen? Its momentum will have high degree of uncertainty. So, we cannot measure both the exact position and momentum of small moving particles. Or you can say here from vice versa, that means if delta px is small, right, if delta px is small, that means the momentum of the particle is known with high degree of accuracy. If the momentum is known with high accuracy, then if delta px is small, delta x will become large. Delta x will become large, and that means that there will be large uncertainty in its position. So its position then will become uncertain. I hope that you all have understood this principle. So now this principle can be explained as see, if suppose we want to find both the position and momentum of electron, right? So if we want to find out both the position and momentum of the electron, so to locate electron we need to use light, right? And you know that, write down, to locate the electron we need to use light. And you all know that light is made up of photons. Light is made up of photons. So when this photon of light will strike this electron, so as a result of collision, both the position and velocity of that electron will change. You can also see from this, suppose that this is the original path of electron. Right? Let's suppose the electron is moving in like this, and here we have this electron. Okay. So now let's suppose that at this instant you want to find out the position of electron. So you will use light. So a photon of light when will strike this electron, if we talk about the expected path, right, we are expecting that the electron is moving like this. So expected path is this. This is expected path. The electron is expected to follow this path. But in actual, what will happen when this photon will strike this electron? Both the position and the velocity of the electron will change. Okay, so it is not possible to determine the both position and velocity of small particles like electron. Now let's see, suppose you want to find, suppose that we want to find out the exact position of electron. Right? Let's suppose that we are interested to find out the exact position of electron. So to find out the exact position of electron, the wavelength of light used, it should be smaller than dimension of electrons. Right? So if we want to find out the exact position of electron, then the wavelength of the light used must be smaller than the dimension of electron. And according to de Broglie hypothesis, you know lambda is equals to h upon p. From this you can also write P equals to h upon lambda. This P will goes on left hand side becomes P, and lambda on right hand side will come in denominator. So if the wavelength of the light used is smaller, so a smaller wavelength means large momentum. So a smaller wavelength would imply large momentum. So when this photon of light having large momentum will strike the electron, so a large amount of this momentum will be imparted to this electron, and as a result of this transfer of momentum, the velocity of the electron will change, right? So the momentum of the light would become large. So this would result in, so a large amount of it will be transferred to electron at the time of collision, and this will result in change in the velocity of electron. So to know the exact position of electron, that means if we want to find out the position of electron with high accuracy, there would become the velocity of the electron would become uncertain, or you can say velocity or the momentum. So if there is the uncertainty in the position of the electron is small, then the uncertainty in the velocity of the electron would become large. Similarly, if you want to find out the velocity or say momentum of the particle with high degree of accuracy, then the momentum of the light used should be smaller. So to reduce if the momentum is small, from this you can say that you can see that if momentum is small, then the wavelength of light used would become large. Then the wavelength of light used will become large, and then if the wavelength of light used is large, then there would be a large uncertainty in the position of electron. There would be a large uncertainty in the position of electron. So it is proved that you cannot find out the exact position and momentum of small moving particles at same time. So that was all about Heisenberg uncertainty principle. Now write down its significance. What is the significance of this Heisenberg uncertainty principle? Write down. Significance of Heisenberg uncertainty principle. So like de Broglie hypothesis or de Broglie's dual nature of matter, Heisenberg uncertainty principle also holds good for all material particles, but it is of significance only for small microscopic particles. Write down. It has significance only for microscopic particles. Right? So it is valid for all material particles, but is of significance only for small material particles. Theoretically, you can also say that if the size, if the object is of comparatively large, if the object is comparatively large, that is heavier body, so when a photon of light will incident or strike on that larger body, then there will be no effect or no effect of collision of photon with that larger body. So it has no significance for larger bodies or macroscopic objects, but has significance only for small microscopic particles like electrons, etc. You can also see this with the help of example. Let's suppose we have an object of mass, let's say 1 milligram. We have an object having mass 1 milligram, that is 10 to the power minus 6 kg. So delta X into delta V, you know, it is equals to H upon 4 pi into M. This is the mathematical expression. Now substitute the values of this. You will get H, you know, 6.626 into 10 to the power minus 34 joule seconds. 4 into pi into mass is 10 to the power minus 6 kg, right? So if you are gonna substitute the units of this joule, you will get 6.626 into 10 to the power minus 34 kg meter square per second square into second, divided by 4 into 3.14 into 10 to the power minus 6 kg. This is the units of joule, right? So on solving, the value will come approximately equals to 10 to the power minus 28 kg. Kg will cancel out from numerator and denominator. Meter square per second, right? The units will be meter square per second. You can also check the units from the left hand side. You know, on the left hand side we have product of position into velocity. The position will have units equals to meter, and velocity have units meter per second. So their combined units will be meter square per second, which is same as we have got from the right hand side, right? So you can see for a body or for an object having mass 1 milligram, the product of uncertainty in position and uncertainty in velocity comes out to be 10 to the power minus 28, which is very small value and it can be neglected. On the other hand, if we have an electron, what will be the value of this product? Write down. Delta X into delta V is H upon 4 pi M. You know, H is 6.626 into 10 to the power minus 34. Units kg. You can now directly write here kg meter square per second square into seconds, divided by 4 into 3.14 into mass of electron is 9.1 into 10 to the power minus 31 kg. On solving, the value comes out to be approximate equals to 10 to the power minus 4 meter square per second, which is of significant value. So from this you can see that if an object having mass 1 milligram, the value of this product comes out to be very small, which can be neglected. But in case of minute particles like electrons, the value of this product comes out to be 10 to the power minus 4, which is a significant value. So in our day-to-day life, as it comes across macroscopic particles, macroscopic objects, That's why we are unable to see this Heisenberg uncertainty principle in everyday life. So this principle is valid for all, but it is of significance only for microscopic particles. And we have proved this with this example. Now, now we will also see that this Heisenberg uncertainty principle, it rules out the possibility of exact paths or trajectories of electrons and other similar particles So this principle rules out the possibility of exact path or trajectories, right, of smaller particles like electrons and other similar particles. How we can see a trajectory in order to find the exact path or trajectory of a particle. Trajectory of a particle can be determined if we know the exact position and velocity of particle at various instants. Right? The trajectory of a particle can be known if we know the exact position and velocity of the particle at various instants. What does it mean? If we know the position of particle, at any instant, right? If we know where the particle is at any instant, and we also know its velocity and various forces acting on it, at that instant, then we can say where the particle would be after some time. We can predict its position, that after some interval of time the particle would be present there, if we know the exact position and velocity of the particle. But according to Heisenberg uncertainty principle, as we know that for smaller microscopic particles, the exact position and momentum of the particle cannot be known at the same time. So for particles like electrons, it is not possible to determine its trajectories, right? We cannot find out the exact path of the electron or exact trajectory of the electron. So this principle rules out the possibility of exact path or trajectories of the electron. We can only talk about probabilities. We cannot use the term exact position or exact momentum. We can only talk in terms of probability, that a probability that an electron may have about position and velocity of an electron at any instant of time. reasons for the failures of Bohr's model of atom. Write down reasons for the failure of Bohr's model of atom. Reasons for the failure of Bohr's model of atom. You all know that the Bohr's model of atom was based on Planck's quantum theory, which considers the particle nature of matter. But we know that the electron possesses dual nature, that is it behaves like both particle as well as wave according to de Broglie concept. So the Bohr's model of atom does not consider the wave nature of electron. It does not consider the wave nature of electron. Or you can say does not take into account the de Broglie's concept of dual nature of matter. Secondly, according to Bohr's model of atom, an electron revolves around the nucleus in well-defined circular paths. Electrons revolve around the nucleus in well-defined circular path. Circular orbits, you can say. We use the term orbits. Right? So according to Bohr's model, electrons revolve around the nucleus in well-defined circular orbits. So an orbit is a well-defined path. Orbit, what is orbit? An orbit is a well-defined path. And you know that a path can be completely defined only if we know the exact position and momentum of the particle, or you can say exact position and velocity of the electron at same time. Right? So a path can be completely defined only if you know both the exact position and velocity, or you can say momentum of the electron at same time. But according to Heisenberg uncertainty principle, we have already seen that for minute particles, you cannot find out the exact position and momentum of the electron at the same time. So this Bohr's model of atom, it contradicts Heisenberg uncertainty principle. Heisenberg's uncertainty principle. Because the orbits are well-defined path which can be completely defined only if both the position and velocity of the electrons are known at the same time. But according to Heisenberg uncertainty principle, you cannot find out both position and velocity at the same time, right? So if you don't know about position and velocity of the electron, then the path of the electron cannot be completely defined. So it rules out the possibility of these well-defined circular path orbits, which are known as orbit. So this model contradicts Heisenberg uncertainty principle, which becomes the drawback for this for its failure. So that was all about today's lecture. I hope you all have understood this lecture. Thank you.